Hi, my name is Kevin Lipovsky. I looked at the paper titled Embark, Securely Outsourcing Middle Boxes to the Cloud. This paper discussed a solution for securely outsourcing middle boxes to a cloud provider. As corporations continue to outsource their IT function, extension to an enterprise's network processing will be considered. The challenge with this is the potential security threat to an enterprise's proprietary data. If the outsourced cloud provider gains access to the organization's network traffic, there would be a security concern. The question is, how can an outsourced third party be able to process traffic for an enterprise without seeing the enterprise's traffic? The paper reviewed offers a solution with Embark. The claim is that Embark will maintain the enterprise's confidentiality by processing encrypted traffic without decrypting it. Embark will also support a wider range of middle boxes and provide competitive performance while providing this required security. The next couple slides will provide some background on Embark. Embark 1 was designed and implemented to allow an enterprise to outsource a wide range of enterprise middle boxes to a cloud provider while keeping its network traffic confidential by never decrypting it. The predecessor to Embark was Blindbox. Blindbox was limited as it only supported the specific class of middle boxes. Deep packet inspection, so only the middle boxes that examine payloads of packets. There were also prohibited performance overhead concerns with the predecessor Blindbox. Embark extends support to a wide range of middle boxes and provides this extension with practical performance. Embark DPI middle boxes DPI, which include parental filter, data exfiltration, watermark detection, intrusion detection. But Embark additional support other middle box classes, including HTTP proxy, cache, and Embark also supports an L3, L4 header, which includes IP firewall, NAT, L3LB, L4LB. Embark reduces the core functionality of relevant middle boxes to two basic operations over different fields of a packet: prefix matching and keyword matching. Embark also provides a new and fast encryption scheme called prefix match. This scheme is superior because it enables the provider to perform IP address prefix matching or port range detection prefix match. It also allows matching an encrypted packet field against an encrypted packet prefix. Prefix match does not reveal the order of encrypted packet fields, which will provide stronger security guarantees. Embark keeps packet formats and header classification algorithms unchanged. For example, an encrypted IP packet is structured just as a normal IP packet, with each field containing an encrypted value of that field. With this unifying strategy of two basic operations, Embark is able to encrypt packet that simultaneously supports these middle boxes. Embark imposes negligible throughput overheads at the service provider. For example, a single core firewall operating over encrypted data achieves 9.8 gigabits per second, equal to the same firewall over unencrypted data. Our enterprise gateway can tunnel traffic at 9.6 gigabits per second on a single core. A single server can easily support 10 gigabits per second for a small, medium enterprise. This next section will provide an overview of Embark. It will include Embark's architecture, threat model, encryption, comparison to Blindbox, and security guarantees. Embark augments the APLUM architecture with a confidentiality protection to redirect an enterprise's traffic to the cloud for middle box processing. The architecture of Embark is APLUM setup with two parties: the enterprises and the service provider or cloud. The enterprise runs a gateway which sends traffic to middle boxes running in the cloud. This cloud may be either a public cloud service or an ISP-supported service running at a central office. The diagram below shows two directive setup from APLUM. Figure A is the enterprise to external site communications. Traffic here goes to the cloud and back before it is sent out to the internet. The second setup, figure B, is enterprise to enterprise communications. Traffic here is within the same enterprise, where the key is known by two gateways owned by the same company. Cloud providers are typically trusted to provide the service, but there is always a concern that these providers will not adequately secure confidential data in the process of providing the service. These threats can be grouped into two categories. Passive threats related to a party that has been trusted to handle data correctly, but who looks at the data and steals or exports it. For example, selling customer data to marketers or disgruntled employees snooping or exporting data. Embark aims to stop these attackers. Active threats manipulates data or deviates from the protocol it is supposed to run. The Embark team assumes that the gateways are managed, trusted, and do not leak information. Embark team also assumes the middle box executes its functions correctly, and since Embark preserves the functionality of these middle boxes, these threat models are irrelevant to the protocols in Embark. Embark decrypts both the header and the payload of each packet so that service providers do not see the information. The header is encrypted because it contains information about the endpoints. After providing a set of encryption rules to the cloud provider, the gateway has a secret key to then generate the set of encrypted rules to provide to the service provider. Afterwards, the gateway encrypts all traffic going to the service provider using Embark's encryption schemes. The middle boxes at SPs process only encrypted traffic. After processing, the middle boxes will produce encrypted traffic, which ESPs send back to the gateway. The gateway decrypts the traffic using the key. Throughout this process, middle boxes at SPs handle only encrypted traffic and never access the decryption key. On top of Embark's encryption, the gateway can use a secure tunneling protocol such as SSL or IPsec to secure the communication to the SPs. The figure shows the end-to-end flow of a packet through three example middle boxes in the cloud. Each middle box operating over an encrypted field. First, the gateway converts the packet from IPv4 to IPv6 and encrypts it. The options field now contains some auxiliary information which will help the gateway decrypt the packet later. The packet passes through a firewall, which tries to match the encrypted information from the header against the encrypted rule and decides to allow the packet. Next, the exfiltration device checks for any suspicious encrypted strings in data encrypted for DPI, and not finding any, it allows the packet to continue to the NAT. The NAT maps the source IP address to a different IP address back to the enterprise. The gateway decrypts the packet except for the source IP written by the NAT. It converts the packet back to IPv4. When compared to its predecessor, Blindbox, Embark provides a broader functionality and better performance. Embark extends functionality to include middle boxes such as firewalls, proxies, load balancers, NAT, and those DPI devices that also examine packet headers. The improvement in performance is attributed to the different architectural setting of Embark. While Blindbox requires 97 seconds to perform the initial handshake for each new connection, Embark needs only to perform the handshake once. With Embark, the connection between the gateway and cloud provider is long-lived. Embark's architecture also makes it easier for end-user deployment. With Embark, the gateway is doing the traffic encryption, while Blindbox required the end host to encrypt, removing the need to the end host encryption, improved deployability because hosts do not have to be modified. With the improved connection handshake performance, Embark can afford to have more extensive security rules while still maintaining performance, converting some regular expressions to a set of exact match string halves the number of rules. While the overall guarantees of Embark are provided in the extended paper, the version of the paper I reviewed provided only a high-level description. Embark hides the value of the header and payload data, but does review some information for middle box processing. Embark reveals more than is strictly necessary for the functionality, but it comes close to the necessary functionality. For example, a firewall learns if an encrypted IP address matches an encrypted prefix without learning the value of the IP address or the prefix. Embark's building blocks include symmetric key encryption, keyword match, and more extensively a new cryptographic scheme, prefix match. While describing these schemes, the paper referred to the encryptor as the gateway whose secret key is K, and the entity computing on the encrypted data is the service provider, or SP. Symmetric key encryption is well known and is used by standard encryption methods such as AES, Advanced Encryption Standard, and was not discussed in the paper. Keyword match was briefly discussed. Keyword match also allows the provider to detect if an encrypted value in the packet is equal to an encrypted rule. It does not allow two encrypted values to be compared to each other. For example, given an encryption of the rule malicious and is a list of encrypted strings, the SP can detect that the rule matches a string but does not learn anything about the unmatched strings. The encryption of the string is randomized, so it does not leak whether two encrypted strings are equal to each other, unless, of course, they are both matched the encrypted keyword. Prefix match allows the provider to detect whether or not an encrypted value lies in a range of rule values. Middle boxes perform IP addresses detection over prefixed or range of prefixes. To detect whether an IP address is in a range, one can enumerate all IP addresses in that range and perform an equality check. However, the overhead of using this technique for common network ranges such as firewall rules is prohibited. Both encryption performed at the gateway and detection performed at the middle box should be practical for typical middle box line rates. Embark's middle boxes do not need to know the order between two encrypted values, but only comparison to endpoints. Hence, prefix match does not leak such order information. Prefix match also provides a protection for the endpoints of ranges. SPs should not learn their values, and SPs should not learn the ordering of the intervals. Encryption of the same IP address in different flows is different because the seed differs per flow. The enterprise gateway redirects traffic between cloud and middle boxes and provides the cloud with encryption rules. First, it redirects traffic to from the cloud for middle box processing. Second, it provides the cloud with encryption of rule sets. A gateway can be logically thought of as three services: the 7-rule encryption service, the encrypted pipeline from the enterprise to the cloud, and the encrypted pipeline from the cloud to the enterprise. The enterprise gateway, data, encryption, and decryption. The paper looks at middle boxes as header middle boxes, which operate only on IP and transport headers. DPI middle boxes, which operate on arbitrary fields in a connection byte stream, and HTTP middle boxes, which operate on values in HTTP headers. Those are a subclass of DPI middle boxes. IP and transport headers are encrypted field by field with prefix match. A source address in an input packet results in an encrypted source address field in the output packet. For payload data, the connection byte stream is encrypted with keyword match. The data in all flows is encrypted with the same key. The reason is that keyword match is randomized and it does not leak equality patterns across flows. This allows Embark to support DPI middle boxes, such as intrusion detection and exfiltration prevention. HTTP headers are a special case of payload data that Embark encrypts the HTTP URI entries using deterministic form of keyword match. Normal keyword match permits comparison between encrypted values and rules, but not between one value and another value. Deterministic keyword match permits two values to be compared as well. Although this is a weaker security guarantee relative to keyword match, it is necessary to support web caching, which requires comparison between different URLs. Given a rule set for a middle box type, the gateway encrypts this rule set with either keyword match or prefix. Embark supports 3 different models for keyword match rules, which allows clients and providers to share rules that are comfortable. The client knows the rules and the provider does not. The provider knows the rules, the client does not. Both parties know the rules. Firewall rules are encrypted using prefix match, a firewall rule containing an IP prefix that maps the 2 encrypted prefixes using prefix match becomes 2 rules. Embark supports the core functionality of middle boxes. In the paper, the focus was on the implementation aspects of middle boxes. These are discussed next. Header middle boxes, which operate on IP and transport headers, include firewalls, NATs, and L3, L4 load balancers. For both read and write operations, the per packet operation remain unchanged. In read operations, the firewall will get the encryption rules set from the gateway to compare directly against the encrypted packets, just as normal traffic. In write operations, the middle boxes assign values from an address pool. It receives these encrypted pool values from the gateway during the rule generation phase. The gateway receives a packet with a rewritten value. It restores the plain text value from the pool rather than encrypting the value from the options header. HTTP middle boxes and how they are supported by Embark is now discussed. HTTP middle box parental filters and HTTP proxies read the HTTP URI as the parental filter observes a blacklisted URI. It drops packets that belong to the connection. The web proxy requires the most modification of any middle box Embark supports. Embark does, however, achieve good performance. The proxy has a map of encrypted file path to the encrypted file contents. Deterministic encryption enables the proxy to use a fast search data structure with index. As noted previously, the traffic is sent back to the gateway to decrypt the header fields and payloads before being forwarded to the web server. Proxy then sends encrypted contents back. Packets are encrypted on a per packet basis so the gateway can decrypt them correctly. Embark supports the core functionality of a wide range of middle boxes, but not all the functionality that an enterprise can consider outsourcing is supported. Some of the limitations of Embark are associated with intrusion detection. Embark does not support regular expressions that cannot be expanded in a defined number of keyword matched. Embark does not support application level middle boxes such as SMTP firewalls, application level gateways, or transcoders. Embark does not support port scanning. The encryption of a port depends on the associated IP address. These limitations can be thought of as a way of improving on the current implementation and will be part of a future work put into Embark. Is Embark practical from a performance perspective, considering the overheads due to encryption and redirection? The evaluation, the paper looked at the enterprise performance and the middle boxes. Evaluation of enterprise performance is shown in the graph. The graph shows the gateway throughput when encrypting traffic is sent to the cloud, first with normal redirection, as used in APLUM, then with Embark's L3, L4 header encryption, and finally with L3, L4 header encryption, as well as stateless HTTP proxy encryption. There is little difference between the HTTP overhead and the L3, L4 overhead, as the HTTP encryption only occurs on HTTP requests. Evaluation, middle boxes. Throughput was sustained for the apps that were implemented in evaluation. The IP firewall, NAT, and load balancer are all header-only middle boxes. The evaluation results showed packet processing over the same data plane, once with encrypted IPv6 data and once with unencrypted IPv4 data. The only middle box for which any overhead is observable is the NAT, which is a reduction of only 2.7%. Embark is a promising solution for securely outsourcing enterprise middle boxes to a cloud provider. Although there are some noted limitations with Embark, as the second generation of this solution, it has shown capabilities that will allow expansion of outsourcing to middle boxes by cloud providers. Thank you.